Good afternoon. Is the slide is visible?
Yes, sir, it is visible. Sir, about the extra class, we can have it tomorrow, uh, 2 to 3 p.m.
Hello, slides are visible. Just a second. Hello. Is it audible?
Yes, sir. It is audible. Sir,
Slide. Yeah.
we needed to have that extra class, right? We can have it tomorrow, actually.
Okay. So tomorrow, which time it is?
2 to 3 p.m.
2 to 3 p.m. tomorrow.
Yeah.
Okay, I will note and I will send the mail. Okay.
Okay, sir.
According. Okay. Thank you. Okay. So just a second. Okay. So in the last class, we talked about the base classifier, or and we see that actually how the Bayes theorem is used for determining the most probable hypothesis class given a data sample. Now you see here, and another thing we have discussed, that from the linear regression, whatever cost function we used is a linear least square fitting. That is basically uh, coming from this kind of Bayesian explanation. So it is possible to give a Bayesian explanation of this linear regression cost function. Okay, so now today we just continue this Bayesian classification and Bayesian learning. So one thing is interesting here, since if it is a classifier in a supervised setting, what is the actual problem? That x is given and x1 y1 is given. So x1 y1 means even. So actual thing is that in this there is some data are given. Okay, and based on this data sample we try to find out a function. Okay, that is our hypothesis function or whatever. Now here these data samples, that the class belongingness of these data samples is also being given. So that these samples are from, let's say, class X, and these samples are coming from class 0 or circle. Okay, so and these data points, so these data points may be multidimensional. So this x1 is basically it may be a vector. So actually it is basically x1 1, x1 2, x1 sorry x1 3 dot 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 x1 n. So this is kind of vector, and correspondingly, and this you can say better to say d-dimensional vector. So it's a d. So it's a d-dimensional space. Here it is a two-dimensional space for it, and there is a one class information. So this is our setting that we know very well. Now the question is that what we can do this basically. We try to find out the probability of x comma y. This is joint probability. Now this joint probability can be, when in case of our Bayes theory, we see that can be written in this way, that P of y given x, this is the capital, and P of x. Now here it is interesting that what we're trying to understand, that given the data, this is the given the data samples are given, what is the probability of a particular data point as y. Okay, so this is the thing. So when we are trying to understand from this is called a very, very important concept called discriminative learning. I just essentially I put this bit of today's thing, but it's a very okay. So most of this classifier we see in our supervised setting, it is discriminative in nature. Okay, so this is the thing. Given x, given a data sample, and some sort of sample and some sort of prior of this sample, can it be possible to find the y? But we can do the reverse thing also. So what we can say, given the class, what is the likelihood of the data? Oh, this is the likelihood of the data. Given the class y. Okay, so this is, so if we try to find out the probability of data given this class, then it's a generative in nature. So it's called generative learning. We'll see that if sometimes when we go to the unsupervised learning, there is a generative adversarial network or other different variational autoencoder kind of this kind of thing. And we'll see what we mean by generative learning. But the major understanding coming from the statistical definition. Okay, so this is very important to understand that. That's why we'll definitely come to this, when we more mature lecture or more, you can say, complicated thing we are going to understand. Okay. So today we'll start the Bayes optimal classifier. So, so as of now, what we observed, I just first reading out, then I explain this thing. So Bayes theorem provides a principal way of calculating condition and probability. So that means what we'll see earlier. That is our Bayes theorem. This P H of D is basically writing here. This is the Bayes theorem, and this particular thing is called a posterior probability. Why it is a posterior? Because this probability, we try to find what is the given the data sample, knowing the data sample, we try to find out the probability of hypothesis function H. Okay, so this is called probability. And then we'll see the map. The maximum a posteriori is a probabilistic framework that find the most probable hypothesis that describe the training data set. So basically we get the argmax of H, that is P of H or T, kind of thing. So okay, so this is the map. But here you see that we trying to find out the most probable hypothesis. Okay. Now we are bit different thing we are saying. So what is base optimal classifier? So look, it is not a hypothesis or hypothesis function. So it's a kind of optimal classifier. That I'm trying to say. What base optimal classifier is a probabilistic model that find the most probable prediction, not hypothesis. Please understand this is very important. Most probable prediction using the training data and space of hypothesis to make the prediction for a new data instance. Okay. So what we required, that what will be the most probable classification or most probable prediction in this case of this base optimal classifier. This is not a kind of most probable hypothesis, but it's a optimal classification. Okay. Now, this is the basic difference, what I'm trying to say. MAP and base optimal classifier. MAP and MLE. MLE is a kind of constrained version of MAP, where the the hypotheses are equally likely, probability of the hypothesis equally hypothesis. So probability is same. So MAP and MLE framework answered the following question: what is the most probable hypothesis given the training data? That we are calculating there. But what base optimal classifier answers? What is the most probable classification or prediction? Same thing. Of the new instance given the training data. तो हम लोग के एक ट्रेनिंग सैंपल से हमारे पास, based on this training sample, if a new sample come, how optimally we can classify it. Okay. So this is called the base optimal classifier. That's the definition of this. So this is different from the MAP framework that seeks the most probable hypothesis. Now we are interested in making a specified prediction. So in general, most probable classification of the new instance is obtained by combining the prediction of all hypotheses, okay, weighted by their posterior probabilities. We'll see this is very important because this is giving the definition of the optimal classification. So the new instance obtained by the combining the prediction of the all hypotheses. So given a prediction, okay, so it is, let's say this is the thing, this is a plus and there is a minus. Okay, these are the two plus. Now ideally there is a point here, so it is a plus or minus. Okay, there's a two class problem that we are going to see here. This is a classification. So how are we going to do? So now this example is given. This is a very interesting example. Now see, there is a 3 candidate hypothesis. So 3 hypotheses here. One is H1, one is H2, and H3. Okay. All these belongs to our hypothesis space H. Okay. That is the basic supervised setting. We have to find out the hypothesis of required hypothesis. Now, what is the probability of given? Probability of H1 given D, it is given. Let's say it is 0.4. Probability of H2 given D, let's say it is 0.3. And probability of H3 given D is 0.3. So what is the map? So what is H map? It's very easy. Then H map is definitely H1 because it is the higher. This two, H1 is greater than equal to H2. This probability of greater than either H2 given D or H3 given D. Okay. So it is maximum possibility. So H1 is the map hypothesis. But now consider a data X. Okay. So what is the data? So that this X, let data X, there is a new data. Now H1 of X this plus. That means it is given plus, it is h1 of hypothesis function is this. So the idea is this. Okay, something like that. So this is since, so h1 is basically plus. So let's see, this is there is the thing. Okay, now this is the point actually. So this is h1. So this is plus. Now h2 is something like this. It's h2. H2 says H2x is minus. And again, H3 is something like that. This is H3. H3x is again minus. That means this. Okay. So now you see H1 plus, H2 minus, H3 minus. The question is, what is the most probable classification of X under this setting? Now, the most probable classification X will be negative. That means even if the map is positive, you see, map is basically h1 is 0.4, it should be plus. But the total thing, why? P of h2 minus d plus P of h3 given d greater than P of h1 given d. Okay, you see. So this is the actual is called optimal. The definition of the optimal classification. This way it is very different than map. So this is very important. Now, how are you going to define it? We understand this is the way we define the optimal classifier. Now, what is the statistical definition of this or mathematical definition? It is definitely we going to understand probability of Vj. Vj is set of all possible class. So let Vj is V1, V2, dot, 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 Vk. So that is the k number of class. K number of classes. So that is for Vj given Hi. So for Hi mean for all i's, I'm going to take this probability. It is the posterior of this. This is the posterior that we know very well. That is the posterior of the given the data. What is the probability of each? This is the posterior of this. So base optimal classification is this. Basically, so we sum it up over Hi belongs to all classes. So all for all Hi, we take Vj. For all Vj, that is also we can say for all Vj. Vj set of, so you can say V, set of V, you can say. Okay. And that is argmax Vj belongs to V. So that thing is basically coming. So it's not required to write here. So all Vj. So this is the definition of the optimal classification. Okay. So here you can see the same example we write in this format. How we going to write it? So you see that PH1D. Now that is why what actually we have to calculate. So this fellow is how many this fellow? This VJHI. So VJ means what? So it's made plus and minus at two classes. This binary class problem. Binary class classification. So plus and minus, two class. So probability of minus H1, probability of minus H2, probability of minus H3. These three we have to calculate. So this is definitely what? Minus H1 is 0 because they said H2 is 1, it is 1. And what is the plus? Another class, H1 is 1, P of plus H2 is 0, P of plus H3 is 0. Nice, whatever. So this is 1, 0, 0. So all these things, because we have to calculate. Okay. So for this, and this we know from our this example. What is the a posteriori H1 given D? It is 0.4. H2 given D 0.3. H3 given D again 0.3. So we just multiply accordingly. And ultimately, if we do this multiplication and sum it over HI, you get 0.4, 0.6. So this is your optimal. Optimal, or let it is maximum because R max. So it will be negative. If you have any questions up to this, please ask. Fine. Okay, so the major problem here, what example we have shown here is a very simple example. So number of hypothesis function is only 3 because these HIs, I is equal to 1, 2, and 3. Now, if this is very high, okay, and then again the problem is classes also may be very high, multiple number of 10 classes, 30 classes, and so it is a very, this particularly we can say this is computationally expensive, or you can say as a technical term, intractable, mathematically intractable problem. That will be a very huge computational cost if H is high. So Bayes optimal classifier, though it provides the best result, but can be expensive and intractable if there are many hypotheses in the hypothesis class, if the hypothesis space is large, big. So we going to approximate. We have to approximate. How we approximate? One kind of approximation we know, use the sampling. We choose a hypothesis randomly from hypothesis class H. Okay, and is called this particular called Gibbs sampling. So approximation, sample hypothesis from hypothesis class H. So what is the Gibbs? What is the constraint and how we do that? Choose one hypothesis and random according to their a posteriori. Probability. And then how to use a new, if we get a new instance, a probability is associated with each of the hypothesis function. And there is a probability distribution over the hypothesis space. Okay, this you know that. Based on our training data or evidence, we get a posteriori probability that is P of HD over the hypothesis space. In the base optimal classifier, each of the hypotheses applied on the test tensors, whatever you see, is the P of HI plus HI of this class, weighted according to the weighted by P of H. It is H1, sorry, H1D. So exactly this is the, and then put a summation and argmax of this. But what's surprising, this is, you see, you have to not go for every, as to just simple one hypothesis H1 among from H. Okay, but the result is very interesting. The error factor of Gibbs algorithm is quite bounded. Even if we take a single approximation, just one, assume a target concept is drawn from H according to prior of H, then the error Gibbs is less than is equal to 2 times error of the base optimal classifier. So maximum error is less than equal to 2 into error base optimal error. This is a huge thing. Only to maximum 2. Suppose correct uniform power distribution over H, then pick any hypothesis from V with uniform probability. The expected error no more than twice the base optimal. So this is the way we solve this particular problem. Okay, so this is called base optimal classifier. So this will end this base optimal classifier, and next we'll show you the another important thing. It's called naive base. So meanwhile, if you have any question, you please ask. Okay. So see what is now naive base classifier is also coming from the base theorem, as you know, that is I'm not the same thing. Now, what is this? What is you have to understand here? As of now, what we said that probability of y, that is the level of which class belonging is, whatever you say, and giving the data sample x. That very beginning we said that x are taking example. X is definitely a vector, and given this x, we have to find out what is the probability of y. That is our primary concern. And the question is that this x will become more practical situation. This x is maybe not a single dimension, it's a vector. So it is maybe x1, x2, xn. Okay, so this is a vector. Now, if we say that from our base theory, this is our base theorem, so we can write in this way: y x, where x is a kind of vector, it is p x bar of y p of y by p of x bar. So this is the thing. So we can say this is the likelihood of the data. So we can use maybe a constant something. So this term is basically proportional to x to this term, x bar y, p of y, where x bar is the attribute of input data x. So x attributes. So you can say attributes. Sometimes we call it a feature, n-dimensional feature space or n-dimensional attribute space. As of now, it's the same thing. Now, if we say this particular thing, if we write it in this way, p of x1, x2, x3 dot xn, this is a joint probability. This is y. So, and calculating the joint probability is very tough. So py, where this is a joint conditional probability, where n is the number of features. That is quite understandable. Again, calculation of joint probability is intractable. Intractable means mathematically or computationally very complex or inexpensive. As for even Boolean valued feature, we have to calculate 2 to the power n number of probabilities. So it's an exponential function. So this is exponential in nature, the number of computation. So now we use the assumption, and this is called naive-Bayes assumption. What is called? Attributes that describe instances. Okay, so that is important, very important. So attributes is a what? These are attributes. Okay, describe the instances are conditionally independent given this classification. So if it is so, we can write it p of x1, x2, x3 dot xn given y. We can write x1 given y to x2 given y dot p xn given y. Okay, into py definitely. This py is there. There's a py somewhere here. Okay. So this is exactly. So we are assuming the conditional independence. So this is called the conditional independence. Among the individual attributes, and based on this we can do the classification. So this is the naive-Bayes assumption, this conditional independence. So all the features are conditionally independent. What is the condition? Condition is this class belonging this y. Okay. So assume our target function. So we basically try to find out that function. This function is basically what? That given x, we have to map to a class B. Okay, where each instance x described by the x instance, particular this is a instance x is, let's say x1. So this is they say a1. So don't be confused, a1, a2, n, since a for attribute. Okay. And what is the number of class? Vj is the number of class, belongs to V. So if we say the V of map, what is the V of map? So that is our old definition. Argmax Vj belongs to V. Okay. Probability of Vj, that is, you can say probability of Vj given the a1, a2, an. Now this is according to your base theory. This is, we can write argmax Vj belongs to V. ये इधर चला आएगा. So A1 A2 dot 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 AN given Vj, probability of Vj by P of A1 A2 AN. Okay, so this thing is constant, so we just omitting out argmax Vj belongs to V. So this term A1 A2 dot 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 AN given Vj, P of Vj. Now what is the naive Bayes assumption? This is equal to P A1 Vj PA2 Vj dot 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 P AN Vj. Okay, so we put it here. So you can write it. This is that multiplication is equal to 1 to j or whatever you can say I P of AI Vj. Okay, so we can just put it here. Argmax Vj P of Vj into this. Get it? How it is coming from all through, which gives the naive Bayes classification from the map point of view. Okay. So here you can say, you can Bayes rule, you can use this particular same thing we are writing actually. So it is P. So y means what? It's a class. So y is equal to, just for example, plus or minus. So it is yk. So yk is equal to y plus or minus. Y is equal to yk given x1 dot 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 xn. Okay. So that what will be the thing? Bayes rules क्या कहते हैं? ये वाले जो चीज है, ये ऊपर आ जाएगा P x1 dot 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 xn y is equal to yk into P of y is equal to yk. ये पहले लिखा है, इसमें लग करके लिखा, and by summation of P y is equal to yj P x1 dot 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 xn. So this is the cumulative probability. So this. Now if we say the conditional independence, okay, so of this, so what we can write, these things we can in the left hand side, and these things we write P of yk, then this sigma, this is sorry, this is pi, capital Pi means multiplication, is P of xi is equal to yk. Just same thing, and नीचे तो डिनोमिनेटर जो है नहीं वही है. So if x new is come, that is x1 dot xn. So what will be the y new? Argmax of yk, p is equal to y is equal to k of this probability. Xi new y is equal to yk. So accordingly. That is where this is called the naive Bayes. Okay, you have any question, you can ask. So before we go further, I just want to ask a bit out of context question. That question I asked a very early or very first slide of today's. That what do you mean by discriminative learning and what is mean by generative learning? Do you have any idea? Because some of you who basically I'm asking those people who have some sort of idea of machine learning or deep learning or whatever, because this is a very, very interesting concept. Even very fundamental concept. So any of you can ask, can just idea what do you mean by generative, what do you mean by discriminative learning. Just for example, this classification. We have already discussed so many classification things. That kind of logistic regression we saw. Okay. And again we saw the KNN classification. Then we saw the Bayesian classification. So different kind of classification we already have shown. So this classification is a generative in nature or whatsoever we have discussed. It is not definitely the whole. Do you have any idea?
Sir, it's probably discriminative.
What please repeat?
Discriminative.
Why discriminative?
Because we are learning our algorithm just for the sole purpose of classifying given examples. We are not generating any new examples.
No, practically your answer is correct, but not very theoretical. Any other clue from anybody? Definitely, we are not generating anything.
So this is this is generative because we are taking the inputs and then we are predicting the labels based on those probabilities. So we take the input that is given to us, and then based on that we take the conditional probability. So that is generative, I think.
No. First you say this is generative or discriminative. Your friend who just answered first, he said it's a discriminative. So you are basically nullifying or objecting his answer that it is a generative. If it is a generative, why generative?
Sir, because it is we are calculating the conditional probability. In this case, we take the inputs and we using that we finally take out the conditional probability for our variable. So that is like we are generating the final result based on the previous.
Okay. So 1, 1. So any other making that track? Why I'm asking, because this is a very, very important and interesting concept. Definitely will come, but in this particular, this is machine learning very fundamental course. We'll definitely next semester will join deep learning. Will go in much more when we basically go for a generative learning paradigm. But here it is. So that idea is, no, it is discriminative learning. Why so? At the very beginning, and so we are in a very kind of fundamental level of understanding. Now, discriminative learning means we learning by discrimination. Okay, as this term sake. Now, when you are saying apple and non-apple, now you are discriminating this apple by its non-apple set. So what we are learning, so for your understanding, it's not that much mathematical, because I'm not going to mathematics in now at this moment, because it will be complex mathematics, or not complex, it's a kind of in-depth visualization is required. So idea is try to understand one thing, the way of learning. We are learning by discriminating, by understanding the difference between apple and non-apple. That's why it's discriminating. Getting the point? So I just go back to my this, not here, but that particular slide where we said how actually we say, given a data x, what the x, what is the y is the level, this is the x, and this is of x. This is discriminative. So the idea is what? That given the data samples, so given the data samples, what we are doing? We are actually what we are trying to, how these two are different. So we are learning the difference between two groups or two set. What we are learning? The difference we are learning. So we are learning how to discriminate between two sets given the data sample. Okay, so that is the why. Given the samples, which is belong to y is equal to y1 and which is belong to y is equal to y2, if it is a apple and non-apple or plus or minus. That's why it is discriminative in nature. Okay. But what do we mean by generative then? Just reverse. That means when we try to given the y, okay. So here you are basically, if we have, we have few example image of cat. Few example image cat, few example image. Given this, okay, given this labeling that it is a cat, can we generate more examples? And more example means more data of cat. Can we generate? So this, in this way it is generated. Okay, so I'm not going statistical definition of this, because we'll go statistical definition definitely when we will come. How actually from one distribution, given a distribution, not knowing the distribution, how we going to generate samples belongs to the similar distribution. That is the generative in nature. So I'm not going there, but at least what I'm trying to say, that is very important. So that's why, given this cat, can we generate? So what is the likelihood of this data? And definitely this is will be the what is the. So this is you can discriminative. And this is generative. Okay, so the very interesting. Okay, we stop here today. We'll carry on this discussion to the next. So tomorrow, which time you said? 2 to 3.
Yes, sir.